The software and programming, these are terms that are used as synonyms. And I'd like to just distinguish them slightly in their orientation. To me, a program is something that runs on a computer. It enables the computer. So when you're focusing on the program, you are really focusing on the computer. Software, on the other hand, is the entity that solves our problems. So if you are focusing on software, you are, and we being humans, you are focusing on the human problem. You're focusing on humans. Why is software important? And we have to realize that on the positive side, software is the closest you can get to an optimal magic that you can imagine today. If you have software, it's infinitely, it's zero cost to duplicate, it's zero cost to distribute, and it's completely flexible, and it's absolutely capable. When it does something, when it duplicates some human action, for example, recording a credit card or moving a credit card number from one place to other, it can be 10 to the 10 times faster. It can be 10 to the 10 times more reliable, 10 to the 10 times cheaper than the corresponding human action. Yeah, those are big numbers. So that's why software is important. But on the other hand, it's hard to create. And the most common excuse for the difficulty of creation software, and I call it excuse, is that somehow it's complex. And we look at that, what's meant by that. And it's interesting that despite of this incredible intrinsic value of software, the progress in improving the process of software creation has been remarkably slow. There's absolutely no Moore's law. There's an anti-Moore's law, if you will, in software. And in fact, I've been using this slide for the last 10 years, and I've been just updating the one on the right. The point here is that this is an actual program from 1963, and which is dated there. It's not a fake program. It's written Algol 60. Probably that was the time when Europe was still in the forefront of software, of computer science. And Algol 60 was a language that, most languages are improvements on their predecessors. Tony Hoare said that Algol 60 was an improvement on its successors. But if you look at it, the kind of the detail of concern, of course, the one on the right is actually is a better program in some sense. It does garbage collection. The one on the left, it does storage allocation and garbage collection. The one on the left does storage allocation, but only on the stack. But if you look at the detail of concern, the kind of attention that the programmer pays, the details are exactly the same. It's the ifs, the whiles, and so on and so forth. And in some sense, I think that the one on the left is better looking. Now we have that was a time when they didn't have the ability to underline words, yet they took the time and the effort. Of course, it turned out that it wasn't that important, so they stopped doing it. It was very expensive to do that on the Flexo writers. So another way that we can see that there are difficulties is by the so-called horror stories. Now, horror stories are pretty important not because they ended with failure. They are important because they are visible. About the only stories that we can inspect are the stories where there was just tremendous collapse or disaster, and then it becomes public, and we can look at it. Another, in this particular case, a particular project done by a reputable company, very reputable company, for 4 years after spending $170 million, creating 700,000 lines of code. It had to be canceled, and everything is thrown away. All the money is completely wasted. Now, a couple of important things about it. For every one of these projects that are that are disasters. There are others that are near misses. And in fact, this project is now repeated. There's a $450 million project that is run by Lockheed that is called Sentinel. And just the day before yesterday, I've read that the FBI is now doing a $1 billion software project for biometric information database. So we'll see how that will work out. But think about it. It's not that there are two interesting things here. One of them is that suppose it had been successful. Still, it's $200 per line of code. It's a lot of expense for the value of an if statement somewhere in the code. And the other one is that when thing failed, nothing could be recovered. And I say, what's going on? I mean, wasn't there some domain analysis done? Wasn't there some design of maybe imagine that there was a list of, didn't they do a list of forms that field agents have to fill out that this particular program would implement? What happened to that? That seems to have value. Well, what turns out is that in a project like this, everything is encoded in a totally idiosyncratic way. Of course, it's encoded into Java or COBOL or what have you, but the way that it's encoded is so idiosyncratic that once it's a failure, it has to be thrown away and nothing can be recovered. So, yes?
About the first one, the $200 per line, it seems like a lot, but how would you know what a reasonable amount was? You just seem to suggest that's high. How would we guess?
Okay, we are getting there. I think that's a valid point. I think that somebody might just say that $200 per line is an okay figure. The point is though that if you think of a line, it does so little, and to say $200 is 1 person hour, and to say that somebody can actually think about that line for an hour is completely meaningless. Now I know that that's not what's happening, but that's what's effectively happening. So that's why I'm saying it. That means that some lines people might be thinking about more effectively, not literally, but effectively. And we'll see more about that. But okay, many people accept it, so like you do, and it's really up to us to think, is that really reasonable or not? There are other here.
How do I get a job that pays me $200 an hour?
No, good point. I'm talking about fully loaded. I'm talking about a government contract, fully loaded, and so on and so forth. No, and look, I didn't want to get into that discussion when somebody says that if I say $50, they say, oh, you're not thinking of retirement and so on and so forth. Okay, so I wanted to be generous. You are correct. So it's 2 hours of looking at every line of code and somehow trying to make sense of it. I don't think so. So there are other horror stories. This information comes from our partner in Europe, the Capgemini. That they know it's their client that remains unnamed here. It's a life insurance company. They had 5 years to do a piece of software that will implement their life insurance, software that will implement the support for their life insurance policies. And of course, they have hundreds of policies and offerings, kinds of policies, not individuals, but insurance offerings. They are complex financial devices and entities. So they work for 5 years. They spend 25 million euros, which is a lot of money, and they still have 100 plans to go. So not clear what's going to happen there. So when you ask what are the causes, and the fun thing is that nobody knows what the causes are. For example, you can go to Wikipedia and there is actually a list there that if you look for the virtual case file project, and there will be a list of causes. And let me just mention some of the causes. One of them is the complexity of code. The other one is that the requirements have been changing, and the third one, which is really funny to me, is that some managers were not software engineers, and to which I can see some other project that failed, and then one of the causes would be that there were no managers who understood there were no one among the managers who understood the subject. For example, there were no field agents, or there were no life insurance actuarials or life insurance administrators among the managers, and that was the cause of the failure. So I certainly don't understand the third one. The first two, I kind of understand what they are saying, but think about it. These are normal events. It's a little bit, imagine if the NTSB, the National Transportation Safety Board, who, by the way, are the most incredible people, and their reports are just the gems of technical writing and the logic. And if anybody's debugging programs, if you want to learn about debugging programs, you should also study the NTSB reports and how they find out the real causes of things. Imagine if a report said that oh, we had this crash, it was really terrible crash, and the cause was that there was fog at the airport, or the cause was that there was icing in the clouds. Well, it turns out that very often the report does say that there's a contributory cause, that there was fog at the airport, or there was a contributory cause that there was icing in the clouds. But these things are normal things. It's not, well, normal in the sense that they are not unexpected. They happen regularly. And airplanes are not supposed to crash just because there's fog at the airport. I mean, we have fog all the time. And so it's really up to us software engineers to look at something that is common and expected, and not listed as a cause for failure. So let's talk about complexity a little bit. And to me, when you look at something that is very complex, it really depends on the description. For example, let's look at scrambled eggs. One way to describe scrambled eggs is a collection of 1,000 little pieces, each one different. And then we would go, the piece number 1 is like this, piece number 2 is like that, and so on and so forth. And that would be one description of scrambled eggs. And you see what I'm driving at. Another way to describe scrambled eggs is by the input and the process. And the input in this case is 1 or 2 eggs and maybe a little bit a touch of salt. And then you apply the process of scrambling, and whatever comes out, that's the scrambled egg. So here we have a description that is much more tractable and much simpler than the other one. So there are many other metaphors that use input and process instead of the description of the direct description of the result. And this is called, of course, the Kolmogorov complexity or algorithmic complexity. In complexity theory, this is why we know that pi is not a random number, because a description of a pi is much shorter. Describing it as an algorithm is much shorter than actually describing the digits. Now, if I may just go a little bit far out, point out that life is also using this kind of algorithmic description. A DNA is describing a process. Or it's an input, it's an input to which a process is applied. And here I'm not talking about, you think that I'm talking about protein synthesis, and I am not. I'm talking about the growing of the organism is the process. I mean, there's the DNA, of course, then there's a protein synthesis. But think of the optic nerve. The DNA doesn't describe the optic nerve as the result. The DNA describes, or essentially starts the description of a process that grows the optic nerve. And this is why we have, so it's the growth of an organ like the optic nerve. And the brevity of the DNA, and you know how brief it is. Our DNA could be stored on a CD. You don't need a DVD. You could store it in an old-fashioned CD, or a dual floppy could, about 2 gigabytes of data. I guess, well, whatever. So about that order of magnitude of data describes a human being. So it's very compact description. And by the way, that compact description makes it possible, makes evolution possible. If we described living things in terms of the scrambled eggs description, there would be no way that any sort of change to that description would yield any useful result. It would just result in a scrambled eggs that is slightly different. But when you change a very powerful description, then you have some chance of doing good form of processing, for example, what evolution does. So why am I saying that? I'm saying this because we could look at software also factor it differently. Instead of looking at the result, if you will, what we call code, let's look at it as an input and a process. And the input would be the domain knowledge, and the process would be the application. It's essentially a computation that mixes the input with software engineering knowledge. And by the way, so under this description, I love refactoring, and everybody should be refactoring all the time. But just for the purpose of this talk, let me make a little fun of it. So this is scrambled eggs refactored. When you have too much salt in your scrambled eggs, what you do is you get a new batch and you apply a different amount of salt, maybe more or less according to your taste. You don't go in with tweezers into little pieces and remove salt crystals or add salt crystals at various places in the scrambled eggs. So to make changes to your software is much simpler, much more direct if you have this short description. You can change either the process or you can change the input. Now, the good news is that I'm not the only one who says that. Everybody is saying this, and this is a big trend, and let's call it the domain orientation trend, and there are all these wonderful acronyms that essentially say the same thing. They mention either the term domain or which is the input, or mention the term generation or transformation, which is the process, in various combinations. So they all boil down to the same thing. But to find out why this is important, and to find out how this trend of domain orientation contrasts with what was going on before, we have to look at a brief history of software. And this is my brief history, or from my point of view. In the 1950s, we had the user and the domain expert and the programmer. That was really the same person, and we'll see a quote supporting that. In the 1970s, starting at '69 NATO conference, software engineering came into, the word was created at that time. The systems were getting bigger. The programmer became a specialist in software engineering, and the programmer was really the only person who understood the system. So the programmer had to do all the work. The domain expert was still there, but maybe as a consultant. So it's a human-to-human communication with the programmer. In year 2000, with domain, we reached the stage where the major value in any piece of software, and you look at any of the examples, including the new releases of Microsoft Office, the value really comes from the domain experts. The value is not coming. You look at the game programs, look at the successful internet companies. The value is not coming from the programmers. The value is coming from the domain experts, people who understand what to do. And how to do things become routine. However, we are still using the old organization because the programmer is the only person with access, intellectual access to the software, to the programming. Programmer is doing all the work, and the domain expert is still a consultant. So nothing really changed. Now, to verify this, I want to show you these quotes from von Neumann's book, published in 1954. And I really love this book. It looks really old-fashioned, but remember the slide that I was showing earlier? That was 64. So the 10 years difference, or 63, so 9 years of difference between this book and Algo 60 was running. It's not a big distance. It's like from it's longer than Amazon has been existed from today's perspective. So there was a lot of changes after this. Von Neumann is, of course, the architect of the architecture, von Neumann architecture of all the computers that we are using. Today, in this book, the word software or programmer doesn't appear. Remember, the user, the programmer, and the expert were the same person. So there was no such person as you didn't have to have the concept of programmer. He refers always to the user. The user does this, the user does that. The user doesn't do software. All the user has is intentions. And that's why we call, that's why we call the company Intentional Software. One more interesting thing there, I don't know if you noticed that the word loaded is in scare quotes. It's a little bit like, Dr. Evil, Austin Powers saying that something is a laser. These words were completely unknown at the time, and of course the loading into memory was a big deal, because before it was fixed punch boards or setups that were used. Instead of program, the word setup is used. It's very interesting to look at, and this is a program from the same era. It's a program on orbit stability calculation. I think you see at the top. It's very interesting to look at. It was written by an astronomer. It's written by the domain expert. Is this astronomy or is this programming? Well, it's kind of in between. Gauss did similar calculations, so it's arguably it's astronomy. But there are elements of computer science in here. For example, notice the blocks. These are the basic blocks that we learn about today, where there are no go-tos in or out. That's exactly what those blocks are. It's also interesting to see what notation people would use if they would have their choice. Because for this wasn't machine processed, obviously. So they could basically use any notation they wanted to. So they obviously chose the one that they liked. And this is interesting in that respect. So, of course, in 1969, it started to go downhill because the machine gotten bigger and bigger, and the problems gotten worse and worse. I mean, more and more difficult. So obviously, well, they were bigger, but not relative to the problems. Those big machines of the time are tiny by our standards. So the programmers had their hands full with problems, and they were there to serve the computer. So they were program-oriented. They weren't, the human needs were secondary. And obviously, they couldn't spend time on representing the domain knowledge or the problem. And I would say that this was in '84, a quotation from Fred Brooks. I call him the prophet of programming pessimism. He wrote this very, very influential paper called No Silver Bullet, the result of which is that anybody who wanted to improve the status quo was automatically labeled a fool, or worse. The complexity of software is taken to be a natural law, kind of the speed of light. And there's nothing that can be done about it, and there's no sense in trying to improve things. Notice in this quote that he mentions that the software engineer must master this arbitrary complexity. Arbitrary complexity, of course, refers to the domain complexity. You know, the complexity of the life insurance system, so the complexity of the guidance equations or what have you. They must master it, and this is forced on the poor programmers without rhyme or reason. What about paying the bills? Is that not good enough reason? I think that it's ignoring totally ignoring the needs of the customer. The many human institutions are the institutions that they certainly have their complexity, but they pay the bills, and we should listen to them. So the outcome from all of this is that we have been focusing out of necessity or out of legacy or a combination of the two. We have been focusing on the least tractable representation of the problem, which is the code. the code, which is the combination of the domain information and the software engineering knowledge that are put together. I mean, this is why the programmers are sometimes called coders. It's because they encode, they encrypt the problem into this really difficult to invert, difficult to process form. It's very, very complex. It's hard to reason about. I mean, you know about proving programs correct, how complicated that is. Let me mention the degrees of freedom. Degrees of freedom just means that how many parameters you have available to you, how many dials you can turn, and in the general purpose programming languages, you always have a zillion times more dials than your problem has. So you have to choose what dials to turn, and of course you can turn them wrong, and those are called bugs. So the opposite of this is if we have domain orientation, then the complexity is reduced. We still have complexity, but now we have where the complexity is factored out. So it's separated. The sum of the domain complexity and the sum of the complexity of the transformer or the software engineering practices that are used is not that great. If you think about the virtual case file project, for example, if you imagine how many problems that a field agent has to face in terms of administration, it's certainly substantial, but it's not 700,000 lines in description. It's probably a manual of the forms that field agents are exposed to is probably not more than 1,000 pages, which is 50,000 lines, say. So it is and then the software engineering knowledge that has to be mixed in. Again, it's fairly routine. We are not talking about research projects. We are talking about databases. We are talking about lists and the like. It certainly would be substantial if it hadn't been done before, but because it has been done before, it's not that great. So the key players in domain orientation are the domain expert and the programmer. And the schema is fairly simple. The domain experts create the problem description, and the programmer creates a generator that processes the problem description and creates the program source. If I may say something about the key players, the programmers, they live in their own world. They see the world through what I call Turing-colored glasses. To them, if something is computable, then that's the ultimate truth. And if something is not computable, then it's prose and it's not an authority at all. The domain experts are very interesting people. They feel like second-class citizens. And nothing frustrates them more than they cannot express their excitement and their passion about the domain to the programmers because they are not speaking the Turing language. They are extremely precise people in their own way, even though the programmers deny that because they say that if it's not computable, then it's not true or it's not precise enough. If you think that an accountant is not a precise person, you are wrong. They are probably more precise than programmers, and they are under more pressure to be precise. So the communication between these two players is really key. The way we organize the production is fairly simple. The domain experts and programmers, they of course have to agree on the shape of the program that will be created. So they have to agree on what parameters effectively are supplied. And I'm using programming nomenclature right now because I'm talking to programmers. So they create a schema which specifies all the parameters that the domain expert supplies, and then the programmer has to still understand what the program is going to do and create a generator that will generate that program. And then now the maintenance can be separated. The domain experts maintains the domain code, and the programmer maintains the implementation through the generator. If you do this, then the domain experts' direct participation becomes feasible. Direct participation means that the domain experts makes a change, a button is pushed, and you get a running program because the generator is run again, and without any need to talk to a human and make mistakes of that kind, you will get a result. So that direct participation becomes possible. Why? Because the domain code is not a Turing language. It's not executable. It's just data. It's given the spark of life by the generator, by the programmer's contribution. So what the domain experts cannot do is program. That's why they are domain experts. So any effort, for example, there was this idea of teaching people small talk. And of course, if kids can learn small talk, then an accountant should be able to learn small talk too. And if this accountant can learn small talk, then he or she can write the accounting program. That didn't work out that way. In fact, I was told by Henning Kagemann, the head of SAP, that he has an easier time teaching his programmers accounting than his accountants programming. In fact, he is doing 100% of one and 0 of the other. There's one more very important point here, is that so we made it possible for the domain experts to contribute directly to the final product, and we also made the work product of the programmer more valuable. I mean, there are two ways to improve productivity. One of them is that you do more of the same in a given time. That's like write more code per 8 hours, 8-hour shift. That doesn't quite work. The other way to improve productivity is to do something that has more intrinsic value at the end of the 8 hour. And that's what we do in our businesses, for example, where assembly line workers are replaced by robot maintenance engineers. So it's probably the same number of people are working there, but they are not putting in the bolts, they are maintaining the machines that put in the bolts. And of course, the work product of the engineer, the maintenance engineer, is much more valuable than the assembly line workers' work product. And the same thing is true for programmers, because what the generator does, it removes all repetition from the programmer's work. And of course, when you do repetitive work, not only the value of your work goes down, but you can also make mistakes. You introduce a lot of bugs, and you get very bored, and so on. So given that domain orientation is this fantastic thing, why is it that it's not, its use is not widespread? And the reason for, this is a key question. The reason that I think is the case is that all of those items on the list, the domain-specific languages, for example, they are still, we are using programming languages as the pattern, as the template for what we are trying to do, and this metaphor of programming languages, I mean, we use that as a basis to create the domain-specific languages and the domain orientation. It leaves these issues. The notation that is supported by the tools are essentially programming notations. It uses syntax, for example. Syntax is another thing that non-programming people have a hard time dealing with. And they already, domain people have their notation right now. Those notations are the notations that they use in their publication, they use in their presentations, they use in their communications to the programmer. They look like spreadsheets. They are not they are not unambiguous. They are precise, but ambiguous, and which is an interesting thing, and we'll talk about that. They don't look like programs at all, and they are used to that, and that's what they would like to use. It's very difficult for them to use syntax. The second thing is this multi-domain notion. No problem is in one domain. Even if you are working with life insurance, there will be a payment system in it, there will be a user interface to it. A problem really is always composed of multiple domains, and combining computer languages is unthinkable. I know that some of you are doing research in that, and just from the difficulty of the problems that you are facing, you can appreciate why it has not been done regularly. It's a research problem for universities. It's a big issue, and just combining two languages, combining n languages is practically impossible. And finally, the evolution. When domains evolve all the time, they change all the time, the world changes. This is one of those things like fog at the airport. It's predictable that there will be change. Computer languages are a great difficulty in dealing with change. You have releases every couple of years, and it's a big deal, and it shakes everybody up and slows things down temporarily. We have to handle change much better, and of course, our proposition is that we have we create a specific tool, the Domain Workbench, that will take that list of problems, and we create requirements from those problems, and then we do a tool that satisfies the requirements, and then we are happy. So that's the proposition. Unfortunately, when we have discussed the requirements, they are really stiff, and so this will be the list of requirements. Documents to be easily transformable. By transformable, I mean that they should be easily readable and interpretable by a program. Remember, we want to do a generator that will read that document at any time and do a program from it. So, for example, identities of things and connection between things have to be very crystal clear to a program. Otherwise, I mean, we can always do a system that supports informal communication between subject matter or domain experts. And in fact, they use Excel to communicate between themselves. They don't use Excel as a calculating engine. They don't use expression at all. They put expressions into Excel worksheets, but they are text, strings. They use Excel as a nice formatting program, and that's how they communicate. They also use PowerPoint, for example. So, but we want a PowerPoint or an Excel that represents the stuff in a way that it's easily transformable. The next thing is that any customary notation has to be acceptable at the same time. So it has to be easily transformable. That means it has to be machine-like. Now we are saying it has to be very human-like, because any notation that somebody used in the past, that should be acceptable. Ambiguous notation should be acceptable, and so on. Of course, you want to be multi-domain, so any part of the document has to be in any domain, which is in any notation. And the domains have to be, you have to be able to evolve them. Therefore, if you make a domain, you can add new things to it, and you want to change the notation. And of course, your legacy, what you have done before, must still be valid. And finally, you want to have a single editing and groupware environment, because you cannot afford, when you have this combinatorial thing of multiple domains and multiple notations, you cannot afford to think of a different editing paradigm for all of them. You could never learn it. So you need a common environment. These almost seem like contradictory. They are almost contradictory. And so let me tell you what we have been working on to bring that all together. We have two particular technologies: the intentional tree representation for the domain we look at first, and then the projectional multi-view editing that works on the intentional tree. And so the workbench is organized by having a database in the intentional tree format in the middle that represents what people are working on. And this can be domain, combined domains, programs, user interface, all of the description of any of those things. And we'll see what the description is like. We use a projectional editor. That means that we don't edit the data directly, we edit a projection of the data that projects it in a form that we prefer at that point in time. And so we have both the freedom of notation, and we have the strength and processability of the data. And finally, so notice the bidirectional, the projection goes both ways, because you project it for the user and then you accept the user's changes to it, and then the generator, of course, creates the target. So that's pretty much what satisfies what we just the big schema. So in detail now, the intentional tree is very much like XML. It's a tree of nodes. So there's a backbone of tree, and then the nodes can point at each other using this identity. Each node has a well, it's different than XML that it's in binary. So it uses very strong mechanisms. For example, for identification, XML uses a textual tag, and the intentional tree instead uses a GUID, a global unique identifier that has the strength of a database for pointing to another node. And these pointers are handled very well in terms of they are not sensitive to their target moving from one place to another. They are not, the target can be deleted, or it certainly can be renamed arbitrarily. They are not sensitive to names. Naming is in particular a property of the projection. It's not a property of the identity. So for example, if I were to change my name, or if my mom uses a nickname for me, that would still refer to me. I'm not my name. I have a separate identity from my name, as opposed to, for example, a textual language like XML. Let me mention one more thing about the offsprings in the tree. When a node has offsprings, those offsprings are labeled, and so that you can always add additional parameters to what you already have without disturbing the existing parameters. And this is in response to the earlier requirement that we handle domain extension. So when a domain is extended, the parameters that have been specified in the past are not going to be disturbed by the new parameters. And everything can be parameterized, and everything can be a parameter. So that one guarantees the ability to represent basically anything. Here's a simple example of, say, from a programming language. It's very much like, in this case, a parsed tree. The domain code would be a node called plus, or a node with the ISA plus. That ISA identity points to another node on the right. Let's see. Here you go. Over here, which is the definition of the plus. And so you can give properties to the definition of the plus, and you can also give parameters or properties to the instance of plus over here. The benefits, I think the benefits are basically that we satisfied a number of the requirements that we have. The parameterization is always possible. We can extend our domain. The transformations will be as efficient because such a tree is very easily processed. Even though it represents a graph, a tree is always very easily scanned by a transformer. So, and let me just mention that perfect groupware is possible because each node has its own identity. That means that when you move a node from one place to another place, we can detect that. It's you can look at the editing operations on the tree and rely on that list of changes to do all the groupware operations that you want to have. Maintain separate versions, ask about who changed a particular node, what was the history of a node, and so on. And you can do this regardless of the particular notation. Now, let's discuss the projectional editor. The reason for the projectional editor is because once we chose this very powerful representation, it's not something that anybody could edit directly. Even XML, poor as it is, I mean, XML is actually in between the requirements of being editable and being general. So the XML is editable, but barely. This structure is much stronger than XML, and it wouldn't be editable at all. So it's important to separate the representation from the syntax, and then you make it editable, and you have this incredible freedom of notation. The editor works both directions of projecting and accepting the clicks. And there are, when you do these things, when you edit a complex structure, you have to have a couple of new type of selections to make sure that you can express the editing that you want. And here are a couple of those selections. In the first row, it's called a crown select. We clicked on the slash and we selected it. Select the top of a tree, and we paste in a times node, and the result, of course, b times c. So we replace the top of a tree by a given selection. If I double-click on the top of that tree, then I would select the whole tree, and that's represented in the second line. And if I paste something on the top of that tree, then the whole tree is selected. And as you see, the result is 2 plus 1. There are two more interesting operations. One of them is called the wrap selection. Wrap selection means that I am trying to operate on C, on the third line. And then I paste plus first, and then 2. The result will be B over C plus 2. Now, notice that the C plus 2 has parentheses around it. And the reason for that is because in this particular notation, the algebraic notation, that's how we indicate the order of execution. But the order of execution was clearly intended by the kind of selection that we did, and it was preordained when we saw what was selected of what the result is going to be. Question?
So is it possible to select the C plus 1 without the B slash in the second example?
The C plus 1 could not be selected as such. That would be it really it doesn't make algebraic sense. It certainly makes textual sense, but there are many things. People often, when you change representations, there are accidental things in the past that you cannot do under the new representation. For example, if you can't, if you use ink to represent the letter T, then you can erase the bar from a T and you get the letter L. But that's an accident of the representation. If you represent text as individual characters, there's no way to remove the bar from T. And if your intention is to replace the T with an L, you do that. So the same thing here. You have to think in what's your intention and do that. Not, hey, I'm looking at a textual representation and I want to change that. Let me just say why that's a good idea not to think that way. Because here we are looking at a different representation for the same expression, or for the same operators, which is the division is instead of a slash, it's now is a fractional line. And notice that exactly the same operations, the same selection modes, and the same paste will get you exactly the same result independent of the notation. And that's very, very critical. Also notice that in this case, the C plus 2 is no longer enclosed in parentheses. Why? Because the fractional line clearly indicates the scope of its action. So in that particular notation, parentheses are not necessary. So being able to edit the same way without worrying about what kind of representation or notation you use is very important. Let me just mention why is it really important to have a large number of notations. And the implementation, by the way, the point of the implementation was that it gives you a combinatorial. This slide showed that there was a combinatorial possibility of different notations that can be applied. And this is important because to match existing notation for domain experts, if you have multi-domain, automatically get multiple notation because each domain, each part of the document that happens to be in a different domain, SQL mixed by C# would require different notation. And the resolution of ambiguity. I mentioned that ambiguous notations are acceptable. Think of a mechanical drawing. A mechanical drawing is a perfectly ambiguous notation. If you have a circle in a mechanical drawing, it could be anything. It could be a hole, it could be a sphere, it could be a shaft, and it could be a ring, many other things. The only way you're going to find out what it is, either you know what it is already, or you look at the object from a different drawing. That's why you have multiple projections in technical drawings. You look at it from the top view, and then you can see whether it was a hole or whether it was a sphere, for example. So the way you resolve ambiguity is by changing the notation, and in both two ambiguous notation can result in an impression or a resolution of the ambiguity. And that's, by the way, how we resolve ambiguity in our human communications. So let me just quickly show you the application example. It's a pension system in Holland. It's a very complicated, constantly changing domain. And now we were in the position where we could tell the domain experts, hey, just tell us everything that you want and tell it the way that it's comfortable for you. And they came up, they opened up their drawers, and we found these fantastic documents that they had. None of which were machine processable. This is, for example, it's an Excel spreadsheet, but it's full of text. And that's what I was talking about. And here are some other document, and here's a third document. And this is the Domain Workbench that is projecting the domain. And in fact, on the right side is projected in a native format. It's so mostly for debugging purposes and for your edification to see that those are the only quantities that are actually stored in the database. The middle column, the left column is a projection of exactly the same data in a format of a table of contents. And then the middle column is the projection that they like to use most of the time. And that's what the domain experts are interacting with. I could brag a little bit more about the system. One interesting point is that all the bits on the screen, including the menus and the tabs and the error messages and all that, they are also projections. Remember, this is a multi-domain projection system. So the domain of user interface and the domain of life insurance, pension systems in this case, are mixed together and done at once. Here are yet another views, for example, a rule dependency view. All of these views are editable. They are editable in a reasonable way, and they all refer to exactly the same data. These are the testimonials. The pension architect is a real person, and he says that before he had to do this mentally and keep consistent in his head. And what he really means is that of course by his head really means that on my spreadsheets on Excel, but there was no help and processing help that was given him, and now he has a direct input to the process. It really changes his life and the other people's lives. The benefits, of course, is the negation of the problems that we had earlier, and the future work is is what we will have to do. We have to complete the work to make the reference customer happy, and then find new partners and new customers and expand to that.
To what extent do you think the domain workbench is domain independent? Sort of universal.
Absolutely, it's absolutely universal. That is the definition of the domain is the work of a client. So both all you have to do is define a schema. A schema can be done in the system, and there was a slide on that I skipped over. That the schema itself is a domain, and so the schema maintenance is done in the system. If there are some special, just by defining a concept, the default projections for that concept, are already pretty good. So you can start using a concept at the moment of definition. You don't have to say anything about it. And that's very interesting. That most of the time what's missing is the ability to refer to something, and express relationships. But the relationships are built into the normal relationships of belonging or relating to, are built into the system. So it's a little bit like UML in that respect, but of course much more flexible, because UML is also a notation, and here you haven't committed to any given notation, and that's a key difference. So we have universality, and you haven't committed to a notation. The particular notation that you prefer can be done by a fairly simple transformation that you will have to write. It's a relatively easy job, and because the system is able to program itself, that transformation can be represented within the system, so you can write that transformation. Obviously, it would be a programmer who would do it, the client's programmer, but the system itself is completely domain independent.